Okay. Hello. Welcome everybody to this, the 20th, already 20th, symposium of the IEEE student branch, PGS chapter in this case. The topic of this year is very special. So there are some, efforts from the European Union to actually push this kind of technologies for many reasons. And what's the idea of this symposium is not only to check what technologies are out there, but also to discuss what are the challenges, the barriers, and how is industry tackling these types of issues. We have a diverse, in this case, panel. And actually the idea is that there is diversity in this technology, and the idea is to discuss in general and to get the insights from everybody. So I will just give a brief introduction on what the student branch is, what we do, and then we can proceed with the talks. We are nothing more than very enthusiastic students that we are here just to, make collaborative events and to bring people, to bring professionals, to bring, in this case, academics, industry, in all these types of events. I'm the secretary, as you can see. And what is the vision? We want to create a big community, a strong community of students and young professionals to discuss energy issues. So that's what we're here for. We have done a couple things. For example, some workshops. We have brought industry experts from different, in this case, disciplines, flexibility services, manufacturers of, ABB, but also, cable manufacturers and all these kind of industry partners, which is very interesting because in the end, I think some of you are from Master Energy, Master in Electrical Engineering, perhaps from other disciplines also. But in the end, we will be all, sharing this very beautiful topic that is energy. And how I like to call it is, how can we bring actually production and consumption? And there is something in the middle. There is something there that we have to work on. And yes, as I said, we have done a couple of activities. So we bring some people from different industries, even, of course, PhD students from the faculty, and just to discuss what is going on, how is their research, and what are they doing. This is, as I said, not the first symposium. This is the 20th already. That's a lot. I was not even here. I was in my home country when this started. Anyway, and we discussed not only this topic, but also cables, distribution lines, transmission lines, design, operation of these technologies. And yeah, as you can see, we bring a lot of people together. Also artificial intelligence, forecasting, and so on. And yeah, without further, let's say, delay, I invite you to follow our pages. You will be scanning a lot of QR codes today, so I hope you get used to it. And yes, what we have today is four very gentle speakers. Yeah? No, I'm not projecting on the Teams normally. There is a link. Oh, that is not possible. Well, I didn't say the technology was perfect. This is one of those things that can happen. Indeed, we decided to change a bit the dynamic, and we are projecting using the K11 resources in this case. So that is why we are not projecting on Teams anymore. But as I was saying, we have four very gentle speakers from diverse disciplines. We're going to start with Agri-PV. What's going on? What is that? How are we going to do it? We're going to discuss about building integrated photovoltaics. And yeah, again, what is that? How do you use it? What are the challenges? The economics of that. We're going to discuss module technologies in this case. And also, what are the architectural and mechanical considerations for these technologies? And I've had the chance to participate in one of these projects of BIPV, and it's interesting to see how the architectural design and how the conception of these technologies is often disconnected from the electrical design. And it shouldn't be like that. And the natural question is, why, right? Why is that happening? So, as I said, they will definitely talk a bit more and more in detail of these topics. So I will just invite our first speaker, Jan Capel from KU Leuven Ghent. And yeah, if you would like, you can applaud also.
Okay, good evening, everyone. I'm Jan Capelle. I'm a professor of KU Leuven, part of the Energyville group, but my campus is the campus in Ghent, where we have about 40 students in energy engineering technology, industrieel ingenieur, for those who know the Flemish name. And we have a group working on sustainable energy technology, and one of the topics that we did quite some research in was Agri-PV the last years. So I want to tell you the story about what we found out. So Agri-PV or agrivoltaics, it's a combination of agriculture and solar energy production. And yeah, it could serve a double goal. If you look from the agricultural part, then we have to adapt to climate change, and especially in the southern countries, there's a lot of problems with drought or heavy weather conditions. But also in Belgium, we had some very dry seasons, and we have to come up with solutions. And maybe Agri-PV could be a solution. From the energy point of view, we need much more sustainable energy than we produce today, or ever increasing need of primary energy, which is for more than 80% still covered by fossil fuels. That has to change. Only 7.5% is covered by renewables. If you look what are these renewables, then you see that it's only, if you look at the primary energy use, only 2% solar energy. So we have to do much better. And we can do it because solar energy has become very cheap today. If you look what happened with the prices from 2010 up to today, we reached numbers below $50 per megawatt hour. Levelized cost of electricity. For those who are not familiar with that concept, you just look what the costs are of your system. So the investments, the operational cost, the maintenance. If you need fuel for solar, it's not necessary, but if you compare with other technologies, you have to calculate the fuel cost, and you divide all the costs by the energy that will be produced during lifetime. And so to know what this means, because it's just, you see that it's decreasing, but this means that solar is becoming one of the cheapest ways to produce energy. And it's a very simple way to produce energy. You don't have to build very complicated systems. You just can build your system with solar panels. And you see the big difference between the rooftop installations. So what we have at home, these are quite expensive. But if you go down the second line, there you have commercial and industrial solar PV, then it's a bit lower. And then if you go to utility scale, the very big fields of solar, there you have very low prices that can compete with onshore wind and are cheaper than the other conventional production methods. But where can we put more solar if we live in a country with almost 400 inhabitants per square kilometer? And if we have open space, it's used by agriculture. So that's why maybe the combination could be a solution. And one way of looking at it is just look at land efficiency. How efficient are you using your valuable land? Let's say you can grow crops, then you do 100% agriculture. I put some prices to know what the value is in euros of what you can win in a year. If you grow peas, seems to be the cheapest crop, 2,000 euros per hectare per year. If you go to rhubarb, then you have 36,000 euros. So that's what you can earn with your agricultural activity. Compared to PV, you can use the same hectares to put solar PV. Then, depending if you look at the market price or if you have a big consumption yourself, you can use it, and then it's even more. That's 360,000 euros per hectare per year, or 75 if you look at the market price of today. So these are two ways of using 100% of your land, but knowing something about crops. I do not know a lot because for all the crop research we work together with the bioengineering department of KU Leuven. But one thing is clear, the more light you have, the more crop you will have. That's an easy law, and that's the yellow curve that you see. I don't know if I can, maybe better use it like this. Yeah. So the more light, the more crop. If you raise your irradiation levels, then all at once there's some kind of saturation. The crop is not using the extra light anymore, and if you still increase the watts per square meter, then maybe you will even burn your crop. So knowing this, it's not a bad idea to use the excess light that is not used for extra crop or extra mass production, to use this as input for your solar panel. So that's the idea. And then you could go maybe to land efficiencies beyond 100%. Look at this. If you combine it, yeah, for sure, you put away some light, so we expect to have less crop. Let's say that we have 80% of the reference we should have if we do only agriculture. You put PV, but you cannot put the same amount of PV as you would do if you do only PV. Yeah, you need to keep some light for the crop, so you maybe can end up with 80%. So one could say this is much more efficient looking at land efficiency, because 80 plus 80 is 160% land efficiency. But we live in a Belgian climate. There is little excess of light. That's what all our field trials show. If we take away the light, we take away some part of the crop. So we have to look carefully if there are possible crops that could be used better than other ones. So there are shade-loving crops that are interesting to look at. And even some crops, like lettuce, for instance, if you put lettuce in a situation with less light, the leaves will grow and will search for light. And if you need the leaves, then it's maybe even a plus to do it like this. And yeah, we started some trials, and we are not alone. The whole PV world is doing trials and hope to find a crop that's perfectly suits the agrivoltaic needs, and so you have all kinds of setups. And there's a lot of discussion about what we will call agri-PV. If you put it on top of grassland, is that agri-PV? For some it is, for some it will never be. So yeah, from an energy point of view, it's a weird discussion. So I would just throw something into the group. So imagine you have 1 hectare of land, and you can choose between deal A or deal B. Deal A is, it's a setup in Hoogstraten in Belgium, where a farmer is growing berry trees below solar panels. The solar panels are semi-transparent, so there are less cells in one module to leave light for the crops. The farmer installed the pillars and the whole construction himself. It's a IKEA concept of PV. So he covered, it's not in the right number, but I translated to 1 hectare. So imagine he has 1 hectare of a berry field covered with agri-PV, meaning in the end he will end up with 20% less berries. The farmer in Hoogstraten is convinced that he will have as much berries as without solar panels. So we have to wait 1 more season, but imagine that he has 20%. I will show our results for the pears, and we had 16% less, so 20% is maybe something that will happen. So that's 1 hectare of berries and 1 hectare of semi-transparent solar covered land. But the other solution is, if you are satisfied with 80% of your agricultural yield, there's another solution. You keep 80% of your agricultural activity, and without solar panels, you do it the way you are used to do it, and the other 20% you cover with solar, but cheaper ones, and you cover with ground-mounted PV. So you accept to have no berries below the solar PV. Maybe some grass, maybe something for the bees or the pollinators. So who is preferring to do A? 1 person? One more? Okay. And are there persons interested in B? Yeah, I'm happy to see that there's at least a discussion. It of course depends. What will you measure? What is important for you? Are you looking at crop yield? You mean kilograms? Or do you mean number of berries? Electricity yield? How many megawatt hours per hectare will you have? Are you looking at crop quality? Maybe that's also an issue. What is the cost per kilowatt hour? Is that important? Yeah, if we have a lack of agricultural land, maybe land loss is an important thing. Or the land equivalence ratio, that's a number to see how efficient you combine the things. It's 2 ratios, one where you look at the agricultural yield, so you look at the agri yield in the agrivoltaic setup compared to what you would have without PV. And you look also at electricity, so it's the 80% I showed you, 80% crops, 80%, so then you have 160%. And you could also look at emissions. And I just tried to translate it to so what we found from numbers, so don't blame me for the correct numbers. It's just orders of magnitude that show how things are going. So looking at the crop yield, they're equal. They both have 80% of the berries of the normal situation. If you look at electricity yield, yeah, for the berries, now it's not the case on the picture, but what we did on the pairs, for instance, was just using east-west configuration to keep the wind load limited. You don't want your solar panels to fly away. So if you go to east-west, you have less kilowatt hours per kilowatt peak. So at the left side, with the semi-transparent solar panels, you have less silicon material, so you have less kilowatt peaks installed per hectare. So in the end, you end up with 630 megawatt hours. At the right side, the ground-mounted system, it's only 20% of your hectare that is covered, so you have less energy, but you end up with 250 megawatt hours. So in absolute numbers, you should choose for A. About the crop quality, it's a discussion with Boerenbond, the farmer, and so Boerenbond is a farmer organization, so it's a trial. So the farmer believes he will have 100% berries, 100% quality, so we will tell you next time. At the right side, we are sure we have 100% crop quality, nothing changed for the 80% crop part. The euros per kilowatt hour, numbers that were, that we found out in the, and that's a bit difficult. Agri-PV, it's, yeah, especially in Europe, it are mostly research sites, so you know that we are not as efficient in installing PV as the market is, so the numbers are, yeah, what they are. 130 euros per megawatt hour, maybe, but that's what we calculated in a European project for Agri-PV. In the semi-transparent case, and at the right side, you end up between 40 or 70 euros per megawatt hour. That's what people in the market are saying about ground-mounted PV. If you look at land loss from the agricultural perspective, maybe the farmer who installed his IKEA system for the PV will lose like 5% because he needs the pillars to put somewhere, so he loses some space. Maybe it's 5%. At the right side, you lose 20%. You offered 20% of your agricultural land for PV. And then the land efficiency, so 80% is covered by, is used for the berries, but you have 5% land loss, which means that you have less berries, so it will be not 80%, but a bit less, 76. And compared to what you could earn on this 1 hectare, you only have 630 megawatt hours. That's 50% of what you could have if you completely cover it with PV. So the land efficiency is 126%, not the 160 that was pretended in the beginning of the presentation. And since you split PV and berries in the right side, it's still 100%. Looking at emissions, yeah, to bring your solar on top of the crops, you will need much more steel, you will need much more material, and that means that your grams CO2 per kilowatt hour will be higher. And numbers that are stated in the European projects that we are involved in, it's 40 grams at the left and 28 at the right side for ground-mounted PV. I have no clue of the time. Okay. So what did we do with KU Leuven? We built some test setups. We started with the system right on top, where one of our master students was trying to grow potatoes at the site of his grandfather, and we were just trying out, will potatoes grow below the solar panels? And they did. And it was a checkerboard. It was an easy system. You use standard solar panels, you make a checkerboard. And I think, Stefan, you eat the French fries that we presented at the end of this trial with the students. And then we went to Bierbeek, to a fruit farmer, and the pear trees, and that's the picture next to it. The lower one is the farm of KU Leuven. KU Leuven has a farm. Maybe as a engineer, we are not the first ones to be there, but the bioengineering department or the bioengineering students, They are there for many trials, in all mainly with animals. But we use their crop trials with steel construction, which is an industry construction which uses a lot of steel that will not be the market installations that you will find in agri-PV. Maybe the right ones will be used or are used. Vertical setup, where you place your solar panels east-west. Then you have solar in the morning, solar in the evening, and you are not using, you're not injecting in the peak production of solar. So in an economical way, it's might be beneficial to put them east-west. And so you see 2 times 3 rows. The rows in the back are fixed, vertical, and the rows closer to you are in a tracking system where we can, in a one-axis tracker, follow the sun from east to west. And I just run through some results. We developed during the project a tool where we can calculate from the PV. I lost my, okay. So we can calculate starting from the PV geometry and the weather data. We can calculate radiation. Normally you're interested in the radiation at the level of the solar panels. Now we are interested at the radiation that is left for the crop, because that is important to know what the crop will do, and also what the water balance will be at the crop site. So we have a complete tool developed. He's available at the website that is mentioned there, and you can play with the configuration. And it's important. We have many visitors. Mostly it's a farmer who was visited by an energy company, and they found a good marriage. You can use my land, you can put solar on my land, and I will grow crops. And if they play with this tool, most of the time, the energy company knows how much solar they have to install to have a viable case economically. And the farmer knows, more or less, I don't know how they know it, but they know how much light they can leave. And then together they discuss, they shuffle with some of these parameters, and most of the time the business case is gone. So we end up with without agri-PV. So this is the story of the pairs. We started, the idea was to replace the hail nets. So the hail protection for the pairs are there anyway. So if you replace the nets with solar, that could also help. Our first idea was, and that's something we are not used to as PV installers, but the pear trees are there for 30 years, and they are installed not taking into account the most ideal orientation for the PV panels. So if you use it as a hail protection, you have to live with the orientation that was chosen by the farmer long time ago. So in this case, it was 25 degrees southeast, which was not too bad. So we wanted the solar panels to be oriented to this southern part. But then we calculated the uplift, and we have to sign a contract with the farmer that we promise that the solar panels will stay in place. So then we decided to go to this rooftop east-west configuration. In fact, not east-west, southeast, northwest. But the lift force was then reduced by 40%. And as a professor, I slept better knowing that this was the case. So we gave up 5% of the energy. And then there was a search, would we go for standard solar panels, which would be economically interesting, or will we make a checkerboard that we learned from the potato experiment, or are we going for semi-transparent solar panels, so panels with less cells per square meter? And you see the light simulations on the left side. That's the uncovered pear trees. That's the light you receive at the different heights of the tree. If you go for standard solar panels, then you end up with far too less light for the growing conditions of the pears. So you cannot use the standard ones. You could use them in a checkerboard, but then you see what happens with the homogeneity of the light. Then you have places that receive a lot of light during the year and places that are receiving far less. So for the homogeneity, we went for the semi-transparent ones. And these are the solar panels that were chosen. 40% transparency, 185 watt peaks per solar panel, still silicon. And yeah, something that is forgotten if you simulate, that is that the backsheet already reduces the part, so the photosynthetic active radiation, the part of the light that is used by the crops, by 10%. So even when there's no solar cell, yeah, you capture 10% of the light with, or you lose 10% of the light. Because in the literature there's a lot of things to do about the microclimate, so we try to measure the temperature in the field. And there we see at ground level that the temperature below the solar panels is always lower than without the coverage. And we have a reference field without PV and the test field. And if you look at the temperature sensors, so the yellow, so the orange and the blue one are the ones in the agri-PV. And there you see during the day we have lower temperatures below the solar panels. And at night, which is important, at night it's a bit hotter below the solar panels. So this could be extra value for the crop. You avoid some of the freezing periods. So that's results of 1 year looking at yield in weight per hectare, minus 16%. It was almost stable. We have now 3 seasons, and it's almost every time 16%. Looking at the quality, no difference. So the left one, the big box plot, is the reference field. So is the that's not right, I think here. As the control at the right side and the agrivoltaics at the left side. So no difference in sugar, no difference in hardness, almost no difference in starch, ethylene. So the quality seems to be right. There was one thing that was mentioned by the farmer, that the pears below the solar panels, they were banded towards the light. And that could be an issue if you need to deliver quality to the supermarkets. That could be an issue. In Grenbergen, we tried the tracking system, and you can change the tracking system according to the need of the plant, of the crops. There are periods in time where the crop needs more light than other ones. So if you know your crop, you can play with that. So that's something that is popping up in research today. We can also do it with our. My time is up. Unfortunately, I have to leave for discussion, but Johan is following a lot of our projects as well. Also, Jens is aware of what we are doing. So, okay, thank you.
Yes, so taking this chance before he leaves, do you have any questions? Don't be shy. Yes?
I had a question prepared for the panel. Yeah. The question I had prepared for the panel for you was actually, what about public acceptation? Yeah? Is that a problem? How do we handle that?
It's a big problem. That's why I was pleased to give companies are telling now, so now that PV or solar is so cheap, yeah, the people don't want it anymore. Especially here in Belgium, we have this idea that that solar was so expensive and we put a lot of subsidy money in it, so we don't want PV anymore. And every time there's someone coming up with an idea, maybe we can cover this field, it's getting a problem. I see that there's this new nuclear thing that popped up yesterday, that our government is promising to dive into the nuclear. Yeah, nuclear is more expensive, it's more difficult, it's more stable if you want to keep your grid stable, but this is a no-brainer. We have to install more PV. And so tell the story and try to convince people that we cannot do anything wrong by installing PV now. It's cheap, it's the best thing we can do. We need it as long as the grid is accepting it, and even when curtailing, because a lot of people are angry because they think by curtailing, and curtailing means that at noon, when everybody is producing solar energy, yeah, you have the impression that you lose solar energy and that you, but also the square meter that has no solar panel, that's the solar you lose. So don't be if you look at 1 year, it will be profitable anyway. So install PV.
More questions? Doubts? Recommendations? No? Okay. So thank you, Jan. We can continue with our next speaker. Stefan de Walef is actually R&D manager at Soltec, and he has plenty of experience in PV manufacturing and integration techniques. And we are also working in a project together with Jens. Yeah, 1 second. I will just give the floor to Stefan.
Okay. Good afternoon. So I'm Stefan, as he explained. I'm working at Soltec, and we are a manufacturer of photovoltaic panels, which seems to be strange. If you look nowadays at the panel price, the standard PV panel, to give you an idea, is cheaper than wood. So if you go to the Brico or whatever, and you buy wooden planks from the cheapest wood you can get, you're at the same price as I can buy PV panels on the world market per square meter, just to give you an idea. So if you want to build a fence, I can give you cheaper PV panels than you could buy wood. So in that conditions, it's what it is. It's just market situation. The prices are below the direct cost. So if you go to standard PV panels, the price of standard PV panels is below direct cost. The big manufacturers, Chinese companies, are losing billions of euros per year by producing PV panels. And that's just a question of demand, market situation. There's a high demand. Everybody knows PV is a rising demand. So they say, okay, then we build factories, but they did build a bit too fast. They are going in competition with each other, so the price gets down. And so that's the market situation actually. And so as a small Soltec in Belgium, we have very high cost, which is logic. We are a Belgian company. We're a small company, so we don't have the economy of scale. Nevertheless, we managed to produce solar panels already since 1989. So it's quite a long time already, so almost dinosaurs. And we do that more and more by going to very niche markets where we have an added value. And that's what I want to explain today. Yep, it works. That's our factory. And immediately you see we stopped producing and selling PV panels. So, okay, closer to the mic. Great, thanks. We stopped producing PV panels. We now produce building elements which have a plus, and that plus is producing energy. And so we don't go in competition with PV panels at all. We go in competition with standard building materials, and these standard building materials have a certain cost. We have a cost that is maybe slightly higher, but you have a large gain because essentially you don't need to build in terms of construction time. Instead of installing another element, you install your PV, so you don't have extra construction time. Maybe you have to do some cabling extra, black and white, but essentially you don't have the extra cost of putting something on top of something else. Also from an ecological point of view, you don't use a material, for example, as a facade element, and then on top of that you start putting another material which then produces energy. So also from an ecological point of view, it makes much more sense. And of course, and that's the most important, from an aesthetical point of view, PV panels are not that nice. You can put them on a roof, fine. If you start putting them on facades, imagine all the buildings in a big city being covered with standard PV panels. It would be crazy. Also from a point of view of safety, I think Mike will talk about it, standard PV panels are not that safe as building elements, which is logic. They are very tiny, 3 millimeter, sometimes 4 millimeter glass with a small sheet on top of it. It's not useful. So what we do is we sell building materials and we produce them customized. We do that in Belgium. We have always been doing a lot of R&D. That's also why I'm probably here, because we have these relations with university, with Energieville to see what we can do there. And we lead to innovation, so that means we're always going a bit ahead of other players in the world market. We are the first to have an automated production. So we make customized automated products, which means we have developed software, we have developed our own machines, where with the software automatically designs the panels. So an architect can come with whatever shape, whatever size, even 10, 20 different sizes in one project, no problem. The software is drawing the PV panels with the diodes, with the junction boxes, everything is really automatically done. And on top of that, we have the machines that, based on that software, automatically knows where to put the cells, where to make the interconnections. So we have built that up, and it's just a preparation for the future. And why were we able to do that? How did we convince our shareholders? Clearly, there is a European law that says all buildings will need to be energy neutral by a certain period of time. It goes, in some countries it goes faster, some countries it goes a bit slower. But anyway, everybody knows that in the future, buildings should be energy neutral. And if you have a large building, you have a small roof on top of a lot of consumers. And in that case, you have no choice, you have to go to the facade. And once you go to the facade, standard panels are not appropriate, as I explained. So there is a market that will grow very fast and will be growing in the coming years. So we are 100% sure that the market will be there. We have the know-how, we have the demonstrators, we have already 20 years experience with BIPV, even more. I think the first BIPV I did was 97 or something like that, so it's quite a long time that BIPV is existing. Up till now, BIPV was just very, very marginal, but now because of this new legislation, it will go faster and faster. So that's what we do. Humidity, for example, this is typical look of a PV panel we make. This is a project called the Vrog. You can imagine why. It's somewhere in the Netherlands. I think there is a picture a bit later in. We have double use, as I explained. We use our PV elements as construction elements for anything. In this case, these are just pavements, yes, with photovoltaic. So you can do streets, you can do a lot of things. Architectural possibilities, and that's going back a bit to how do you sell it now? At the moment, of course, the volumes that we can produce are not that big. The capacity we have now is about 80,000 square meters per year. It compared to standard PV, that's small. So we are looking for, let's say, nice project where we have a lot of added value and where we can, of course, make margin on our products. We are a company, we need to gain back the investments we did, and that we do it by doing very nice projects with architects, where you are in a market segment where anyway the price of the building construction materials is quite high. If you compare our panel to, let's say, bricks, then we are expensive. If you compare our panels to marble, steel, whatever facade elements, we are cheap. So we are somewhere in the middle, but we have that extra energy production. We also, our building elements meet, of course, all construction standards, and that's quite important. So we have a whole list of certifications, and part of these certifications are just building certifications, and only the last certifications are really photovoltaic certifications, because for the most of our clients, which are facade builders, we are construction companies, they don't even know about certifications of photovoltaics. The facade you see here is a LED facade. It's another product that we make. We do, of course, just in time. So that means in construction world, it's totally different. And that's something that we had to adapt ourselves. Let's say 4 years ago, we took the decision, okay, we're going to make building elements. And that's a totally different world from the standard electrotechnical materials. Electrotechnical materials, you produce them in large quantities and you try to sell them. What we do is we sell something, and once the order is in, prepayment is done, we start producing it. So it's a totally different world, but that means also that you don't have stocks. You have to react to orders. And so you have it's a business, it's a project business, which means it goes up and down the whole time. So it's a totally different management of time. And it's also just in time because, for example, when we did a big building in the Netherlands, 27 floors, we have to supply every time 3 floors because they have their construction work going on floor by floor, and you have to follow them. If they go a bit faster, you have to produce faster. If they go a bit slower, you have to slow down your production. You have to adapt to your client because, you just cannot store a lot of elements on the field. Cost can become a revenue module. If you look at the payback times, because that's a question that certainly will come later on, so I answer it immediately. At the moment, we have a payback time, if I look at the additional cost of PV, of about 6 to 10 years. To take a large gap, depends a bit on type of product. That means that the additional cost our clients put in having a facade element that is active instead of a passive, we have a payback time of 6 to 10 years. Seems a lot, but if you have to imagine in the building world, we are talking about lifetime of a building, 30 years, 40 years. And I want even to go one step further. We have a payback time for the facade total element of 20 years. And then you say, well, 20 years is crazy. And then I say, no, at least you have a payback of your facade element. If you build a facade with other elements, your payback time is never. So in that sense, and as your lifetime is more than 20 years, we give even 25 years warranty, there is no issue. There is essentially, it's a no-brainer. You should install PV. So that's certainly, we have these certified things. We do materials with a plus. I'm not going too much in details there. The build-up of our materials is very similar to a standard PV panel, except that most of the time we don't use a back sheet, we use glass at the back. So we work in between two glass sheets. We can, of course, also go to IGUs, so insulated glazing units. But let's say the build-up is quite normal. Where we are different from, let's say, a standard manufacturer is, besides that size, that we can play with these layers. You have different glass layers, and we can use colored glass. We can print on the glass. We can make the glass very thick if necessary for mechanical reasons. So we can really adapt these sheets. We can use whatever materials we want. Most of the time we use glass, but you have choices there. Of course, our clients are interested in what we do, also from an energy point of view. And I put in this slide to show that, okay, of course, there is a lot of potential, that's for sure. But also, by using the facades, we are working vertical. And if you look at it purely from a kilowatt hours point of view, energy point of view, we produce less than people producing with their panels at 35 degrees, logically. But we produce, in wintertime, we produce better because then the sun is low. We very often have facades on the east, on the west, so we produce in the morning, in the evening, rather than in the middle of the day, because you probably know, I don't know just your background, but in the middle of the day, energy prices are below zero. So we prefer our clients not to look at the kilowatt hours they produce on a yearly basis, but what the value of that kilowatt hours are. And the better you can match your own consumption, the better performance you have from an economical point of view of your system. That's a bit thing here, but I think these kind of graphs are very clear. By using different surfaces, you spread your production over the day, you bring it more to the morning, to the evening, which is very beneficial in terms of economical efficiency. We have different types of integrated photovoltaics, building integrated, vehicle integrated, infrastructure integrated, product integrated. I just do some small things. Product integrated, we already have them very long time. For example, in the middle above, the picture there is about beaconings at sea. And there, we have done them beginning of the 90s, so about 30 years ago. And then PV was very, very expensive. Nevertheless, we did these systems because the client had no other choice. Then we went to things like, on the right-hand side, parking meters. We were the first worldwide to make parking meters photovoltaics. And then we went in competition with connection to the grid. But if you have a small consumer, you have to break up the floor, make your connections, all the contracts around and things like that. Photovoltaics was much more logic. And nowadays, I think worldwide, almost all parking meters have solar integrated. And so we went slowly further. And then, of course, grid connection became feasible because of subsidies. And nowadays, grid connection is possible without any subsidies. There's no need for subsidies anymore, as explained by the previous speaker. PV is one of the cheapest methods. And by combining it now in the building materials, it can even go further. Vehicle, I will not stop there. There you see, for example, on the right-hand side, you see a bicycle path. So you can imagine bicycle path, photovoltaics. Bicycle paths are, for the moment, not profitable yet. That means that the payback time is too long to be reasonable at the moment, but that's a question of time and investment and developing further. Then we go to integrated photovoltaics in buildings. Facades, you see we can do colors, you can have very often we have done a lot of sun shading elements, because then you combine functionality of sun shading, and then you do not even have to look only at the photovoltaics, the performance of the photovoltaics. You also have an effect, of course, on your building. You have on your HVAC, on your consumption, and you have to be careful. If you put too much solar, then it becomes too dark inside of the building, and then you need again more light. So essentially what we do there is, together with engineering companies, you look at the total profile of the building over the whole year, and then it becomes quite complicated, and that's why I'm happy to speak here. The coming years, for me, the biggest challenge will not be to produce cheap energy. The biggest challenge will to be at total system level, to manage the energy flows, when do we need energy, when will we consume, how can we steer, or how can we, let's say, shift some consumers without using too much batteries. And that whole energy system management is something that we will have to do at grid level, but certainly also at household level, at building level. And that's a really huge challenge, because it looks easy, it seems easy, but in practical, there's not enough knowledge yet spread to be able to do that. So there, you guys will have to do it the coming years to help us out. Roofs, these are well known. Canopies, already, like for example, on the right-hand side is some pictures from a market square in Mortsel, where already 15 years ago we installed large 1,300 square meter semi-transparent panels. I skipped one, Second Skin, on the right-hand side, for example. It's in Barcelona. It's really a second wall, so it's really it's a renovation project. Here, all the black parts you see are photovoltaic panels. It's in Brussels, and you don't see it. I mean, just to be clear, we do that, and you cannot see it at all, because it's a black panel. You don't see any lines, you don't see any connections. It's just a black panel. The squares are well known, and then slowly we come to the black part. You see right-hand side above also black parts. And maybe here, that one, for example, here, all the black parts also of that building are photovoltaics. And then we can even make white panels, and then we come to another question. It's always asked, yes, because of that color, you certainly have lower performance, and that's correct. If we have typical colors, we lose in between 10 and 30% of energy because of coloring the PV panel. When we go to white panel, we even lose 50%, which is logic, because white is essentially the whole range of radiation that you reflect. But for standard colors, let's say we are about 25, 30. For optimized colors, special dedicated layers that we use, we lose only 10%. So more and more, the last 2-3 years, we have a lot of projects where we lose about 10% compared to a black panel by using colored coatings on our glass. And that kind of things. And here you see some examples. On the right-hand side, again, our building with a nice picture. So the big picture there is photovoltaics. You cannot see that it's photovoltaics, but it's a nice picture of photovoltaics. In the middle, you have some logos. And then just from references, I have no idea about the timing, but so we can go to some references. This one, I put it first as picture because it's in Brugge. And so now we see that even in protected areas, because Brugge is an UNESCO protected city, you can call it like that, even there we manage now to sell our PV, because we really adapt the surface, the reflectance, the colors to what our clients are asking for. For example, there's now a building in Brugge where we have to do a recladding, so it's the cladding needs to be removed and needs to be replaced by photovoltaics, and there we really go in negotiations with UNESCO and other organizations, control organisms I call them, because for us they are really very close by checking what we are doing, and so we need to prove that it's not visible and that it's integrated in the architecture around us. So that was the first one. Here you have the frog. You have seen the picture there, and so that looks like that. It's in the Netherlands. They like more or less shiny colors, so why not? We can do that. I'm pushing on the button up. No, it was not following. Yep. Here you see balconies, typical. Balconies are very efficient because a lot of buildings have them, and you can use parts of your facade without interrupting too much. This is then product integrated, of course. So this is train stations in the Netherlands. We have done a lot of them. Bicycle path. This is a typical project in Brussels where we do on several parts of the building, we do photovoltaics. So the black parts of the big building are in photovoltaics. There are shading elements. And also in the greenhouse, the roof of the greenhouse is semi-transparent panels. So you combine on different places on the building photovoltaics, and you manage to have a quite high percentage of the building supplied the energy by your photovoltaics. And that's really what this is a project that I like, in that sense that you really combine different installations, even on the same building, and you don't see it. The semi-transparent, you can see it. If you're inside there, it's huge. I mean, this is you see the small people running around, so it's really a huge, huge greenhouse. Don't imagine just a small greenhouse. But the roof there, you can see it. You see the dots of the photovoltaics at 20, 30 meters high, so it's not that it's annoying. This is on the project in Bolt where I talked about, with the black, so all the black parts there are photovoltaics. We have seen that one. This is private home, and I put it in just to say that at the moment we don't produce that much for private homes because you have an engineering cost, you have a startup cost and things like that, and we are evolving, and so the coming years we will slowly come to private houses, but and that's one of the things that I never understood. From a company point of view, we have developed slates for Eternit, ATEX Group, we have developed tiles for Wienerberger, Ceramic Group, so for big manufacturer of slates, of tiles, we have developed products, and they never were a success. So we have developed them. The price was lower than what we sell now. So no discussion, lower than what we sell now. So the payback time was lower than what we do now. But it was never a success because somehow the market is comparing these products to standard PV on top. And then you lose the battle because the ROE, the return on investment of a standard panel is better. Yeah, okay, fine. And now? And that means that you cannot scale up to high enough volumes to be competitive with these standard panels produced at high volume. And that's why we have chosen that way of making, let's say, the more complicated and coming from the high-end product and slowly getting to more standardized product. And so the coming years, with automated productions, we will slowly come to more standardized products, but a really fully standardized product. Also, and then it's like it is, for Soltec it would not make sense to make a fully standardized product, even if it's BIPV, because then you produce 100,000 of square meters, and then you can be sure that some guy will copy it and do it cheaper than you can do it here in Belgium. So that's why we still make these complicated modules, and that's why you cannot find at the moment reasonable slate styles on the market. It's because that market gap is there. And it's not technical, it's really market barrier to introduce this kind of product. It will come, but it takes a bit longer, apparently. We have seen that one. We have seen very nice shapes with things. On top of that, maybe interesting, for example, in Brussels, they really need PV. They also have the same target as everybody, but in Brussels, of course, yeah, there is no free area, essentially. So they made an exception, and although you cannot build higher than a certain level foreseen in Brussels, if it's PV on top, in a kind of structure which is more or less open, they allow us to go one floor higher than was foreseen for that building. So that's why in Brussels we managed to do some project, and you see there, it can be nice. Huh? These are some stupid tiles, and this is indeed something that we try now, and we see what comes out. Because maybe there we can have an easy introduction in the market, not by selling ourselves to the end market, but selling through companies that are doing pavements, essentially. And then around the world, I will go faster. This one is a nice one. I like to show it because there you can imagine all panels are trapezoidal. So essentially, if you look from the bottom to the top, all panels have a different size and shape. So that's really, from an engineering point of view, quite challenging. From a logistic point of view, you can imagine they have to be in the right order to be installed, because if they make one mistake, everything goes wrong. So that's quite challenging. But these kind of projects for us, for the moment, are the base of our business, because you can imagine that a client like that, 10 euros more or less per square meter, it's not really the concern. I mean, it's a negotiation, of course, that needs to be done. You have competitors in the market. We are not alone. There are few companies able to do what we do, but there you have added value. Some pictures like this. It doesn't always need to be a lot of photovoltaics. Huh? This is in Norway. You see that there are just scattered cells. So it's, again, a second skin with not too many cells, but it's nice. It's great. And this is then typical in Paris, where you have the roofs, different shapes, different sizes, covered with photovoltaics. This is in South Korea. And there you see you have the black parts of photovoltaics. You have the O around at some windows, and then you have some windows which are more filled with photovoltaics. So you see that different parts, again, are covered with photovoltaics. To give you an idea, for the moment, we produce exclusive products, and we ship worldwide. 1/3 goes to the US, 1/3 go to Asia, 1/3 stays in Europe of our turnover. Europe will become more important, I guess, when we have the growth of market, but at the moment we're really looking worldwide. And we can ship worldwide because there are not so many companies that can do what we do. Some very special shapes, something standard, and that's something that we sell, but you see only in Switzerland. So the tiles we produce, we have one client in Switzerland who has kind of PV tiles. You see the terracotta things in the pictures, but that's because Switzerland are really ready to pay more money to have a nice integrated system because they have the money. But from a company point of view, I don't care what the reason is. As long as I can make the margin, I'm ready to go for that market. These are gladiolets. I will not get on that. We also make product which is glad elements integrated in a glass panel. And that's, again, from a company point of view, I explained that we have that project business. If I combine two project businesses, I have a better flatten out of my production. So the same people can work on both products, same equipment can work on both products. And so what you see here, the small dots are LEDs that we integrate in the glass. And then you can have at night the nice pictures. I think this one, it's even moving. You see on the left-hand side, you see the daylight, and the night you see the screens which are lighting up. So there are just, I think, lobby rooms or whatever behind and there at night it looks like that. This is again, you see, clients can be anywhere, and this has been filmed by hand because in Turkmenistan you're not allowed to film what you are doing. So, and so there let's say the client wanted to have running horses over its building. And that these are the LED panels. We combine LED and PV because essentially from a technical point of view, production point of view, it's very similar. Both are diodes, you have connections, you have cabling, you have lamination process. So for us, it's a very similar product. I think I will pass through this kind of pictures. And this is a project now, we are busy now in the US where we have the leaves are photovoltaics, the G's are glass LED products. So we combine in one very big building on several places PV and photovoltaics. And so there we have a client where, let's say, almost 75% of his cladding is supplied by Soltec in active glass, glossy LED, or photovoltaics. That's it. Try you can see the pictures of this was the rendering of how the building will look like. And I'm finished. I have no idea about the timing, but time's up, yes?
Yeah. Okay, thanks a lot. Before going to the break, are there any questions? Yes.
Thank you for the interesting presentation. My question is, are you operating more in the space of only new fittings, or are you also considering retrofittings? Because I think this mostly works when you're building the new buildings.
Mostly new buildings.
Right.
Really, because then you can work with the architects and you have for the bigger projects, you have a time of about 5 to 7 years between first contact with the architect and the real installation of our PV panels. So
Yeah.
more logic for new buildings. We have done some research projects where we really work on recladding. That means that you can really replace existing materials by new materials, or you
Can I ask?
and most of the time it's not just the PV, it's PV with insulation with, so you really create in the factory total building elements with all the components that you need
Yeah.
to have a nice building element. PV of course goes out of all components and integrate that in total. There are some projects, research projects now where we start doing that, but it's a huge challenge and it will be probably one of the big challenges for the coming decades, because we have a huge amount of buildings which need to be recladded in the coming years. We want to do it, but for us as a manufacturer, it's not the easiest market to get.
And if it's mostly for the new buildings, do you do this kind of load flow analysis, which you mentioned, that so that the overall HVAC efficiency gets improved? How, do you also look at the flexibility market potential as of now, or you don't? For now, it's just mostly.
It's not our job. We assist, of course, because we have part of the knowledge, and then you're more in the job of the engineering companies to really look at indeed what's the consumption profile, what's the production match? How can we, but it's not a job of Soltec, we are a manufacturer, but our clients most of the time are assisted by engineering companies which are really good at that kind of things. And at IMEC, Jonathan, for example, they really create these models to calculate exactly what, when, and these can then be combined with the day-ahead prices on the market. And then I'm in the field of Professor Driesen, I think, because that's indeed what also at Soltec now for our building, because our building is, let's say, more or less self-sufficient on a yearly basis at least. And there indeed we do pricing day ahead. We look at production, what our production needs for tomorrow for our production, what will be the production of PV. We try to combine, and we indeed shift with the HVAC, with the heat pumps at the moments that it's necessary. And that total, that's what I said, that's the system engineering, where the coming years there is a big need that will have to be filled. And the knowledge there is something, from a theoretical point of view, we know it. Practical, there are not so many companies able to help you there, but it will come because it's necessary.
Regarding the amount of electricity generated, so how much of the load was covered based on these additional intelligent classes which are generating?
It depends from project to project, but the most efficient project that we are doing now, we come to a zero energy building at yearly base. Because these are the zero energy buildings where we cover the part that is consumed, because you still have consumption by our photovoltaics. So we come to zero energy at yearly base, but then you really fill the facade. It's not just a few panels then, which is fine for me, of course. But we can come to zero energy buildings, but there again, it's at building level. So that means that also the light, the heat pumps, everything has to be studied very well to reduce the consumption before that we come. And that's always what I say, the best energy is the ones that you don't consume. So it makes our life easier to get to a zero energy if the rest is well done. And so and it's very often negotiation with the client. So we had lately we had a project where we needed that zero energy, it was imposed, but then they wanted a nicer color, brighter color. When we go to a brighter color, we lose some energy. And so they had to install, let's say, more expensive light inside of the building to reach that zero energy, because I could not comply with the surface I had to the demand of having that zero energy. So that's why I said that's a total system that has to be looked at. And then, yeah, you have to make concessions in aesthetics, in surface, in cost, of course, always. That's a bit, yeah, the world that I'm living in. Yep.
In the beginning, you showed us the slides where there was also a closed air layer behind the PV layer in the design of the building.
For semi-transparent panels, we do that quite often, yes.
But we all know that the efficiency of the PV will lower when the temperature of the cell increases. Is there some further research or plans for integrating natural ventilation or centrifugal other plans for
Yep.
increasing cell temperature?
It's correct indeed. So most of the facades that you have seen are ventilated facades. So we normally go to ventilated facades if we can. And it's not only because of the performance, because your performance drop is there. It's correct, but the performance drop is there, let's say in full sunshine when it's very hot and everything around, and then your PV anyway produces more than enough. Then we even have to shut down some installations because it's producing too much. So that's why we don't care too much. And on a yearly base, it's quite reasonable what you lose. For example, we have done that measurement for integrated tiles from Wienerberger. We installed 2 installations next to each other, open on top and really integrated in the roof. And on a yearly base, we lost about 3% because of that integration. And 3% for me is nothing. I mean, next year, our systems are 3% better than this year. So you're running 1 year behind in efficiency, which is nothing. So we don't care there too much. What I'm worried most about is about the temperature building up in all your materials, because we give 25 years warranty, and if we're building up high temperature in your materials will suffer more. It's a quite linear, let's say, temperature and what you have as suffering from your materials. And so I'm more concerned about that, and that's why we always calculate, and it's purely thermal calculations, how hot it will get. And in some cases, indeed, like in the semi-transparent modules, we cannot fill them too much with cells, because then your air gap between the both would get too high, and you would have problems with your ceilings and things like that. It will work a bit on your performance, but certainly for vertical panels, it's quite reasonable. So it's a mixed answer, I know, but performance is not that much of a concern. Of course, it needs to be performant, but this temperature effect, we talk about a few percent more or less. And if you really have a very tight business plan with an ROE, which is very nice calculated, and you have banks behind everything, then that counts a lot. If you go to a building, you're in a lot of scale of dimensions, and then a few percent more or less are not that critical. Shading then is much more of a problem than overheating of your panels. And indeed there you take in account, and for example, the building in the Netherlands, we started from 27 up to the 4th floor, and then we stopped because of shading, because we had enough. And then if you have enough anyway, you start from the top and you do start from the bottom with your PV. That's then the shading issue. And shading elements, I'm looking at Jens, you can also solve them by using smaller inverters, having the right cabling dimensioning. And that's why you have seen these pictures with all these colors. That's typical, the pictures that are made to try to combine PV panels that have the same installation over the day, because then you can, and that is a system optimization. That's also part of our job. It's not that sexy, but it needs to be done also. Long answer for a short question.
I feel that is a very hot discussion. However, I will, for the sake of time, I will ask you to save your question for the discussion. Keep it there, write it down. We will have a very short break. Very brief before we start, I promise that you will be scanning a lot of QR codes today. This is the first one. So take 1 minute, perhaps 2, just to fill in this small survey, because we want to understand what type of events you want, but also what type of topics you want. What is the format? You know, with these new generations, we don't know, right? So actually, that is the reason why we want to understand a bit better. It takes 1 minute if you fill it in very fast. And that is it. I will give you just a couple seconds. You know the rule of big numbers. We need some dozens of those. No, joking. And yes, without further delay, I would like to introduce you to our next speaker. His name is Jonathan Hovarts. Hovarts, right? I pronounced it correctly. He's from Ghent University, senior researcher at IEEE, EU Hasselt, and Energyville, and he has extensive experience in module integration and construction. So I will just give the floor to Jonathan.
Yes, thank you. I hope this is working. Good, yeah, thank you. Okay, good evening. So indeed, my name is Jonathan Govaerts. I work for, well, I work at IMOMEC, which is basically an associated lab of IMEC at the University of Hasselt, and we're located in Genk, in Energyville, which is again a conglomeration of research institutes where also KUL is involved in. And so I have a background in PV module technology, and the last years it has a growing topic has been integrated PV, like we have been discussing as well. Okay, sorry. And so the last years there has been a growing interest into integrated PV and multifunctional PV, whatever you call it. And so in the following slides, I would like to discuss a bit our learnings on that in terms of technologies and considerations around these. So, but first, from a PV perspective, maybe I want to start with this, let's say, the standard PV modules and the market evolution. So, you see this graph from German Institute Fraunhofer-ISE, and here you see how exponentially the production of PV modules has evolved over the last now 25 years, let's say. And you see we're at about 500 gigawatts of PV module production. You can also see that by far the majority now is monocrystalline silicon based. There's a very small amount, still like 2.5%, which is thin film based, and that is basically all cadmium telluride, so First Solar producing this. And if you look at where these panels are made, they're by far made in Asia. So current PV modules on the market are typically monocrystalline silicon made in Asia. Now, if you look at, for example, the numbers of last year, 2024, there you see the number of modules shipped. So that's 663 gigawatt, and you see the different colors are the different companies making them, and you see the 4 biggest one make around half of the amount of PV modules that have been shipped. On the other graph, you see all the capacities of the different companies with a certain production capacity, and you see that the total capacity reaches over 1,000 gigawatt per year. So basically, it's a bit what Stefan said, that there's a lot of overcapacity in the market, which is part of the reason why the cost is so low for PV modules. But luckily, so if you look at the ITR-PV roadmap, which is the roadmap that is laid out for the technology, then you see that there's still room. You see that most of the standard PV modules are made for power plants and for rooftop application, residential. But those are standard panels, let's say, standardized, but still there is a growing amount of modules that will be adapted for niche applications, and these is what we call integrated applications, like floating PV, AGPV, building integrated, and BIPV, and you can think of others as well. So that is what we will be discussing about in the next slides, and of course, if you go to these kind of integrated applications, you not only have the requirements from a PV module perspective, but also the requirements of the applications, and that I will go over them in the next slide. I don't need to state them here. I will come back to that. So looking at the technology, okay, very basically, you get photons. They go inside the solar cell. That is basically a diode. You catch out the electrons, and you have some waste heat in there. And so that's the heart is the solar cell, the crystalline silicon solar cell, and then you implement it in a module, also like Stefan showed. Typically, you have a glass encapsulant, and the crystalline silicon cells that are connected in series, another encapsulant, and a backsheet that can be glass as well in a growing amount. So they look like this. Everybody is aware of this, and they are implemented typically on roofs in residential applications or on utility scale in these big fields. And so for the energy transition, we want to look at massive deployment of these PV modules. And so in this slide, I would just like to take a bit of time just to give you some rough numbers. And again, like Jan also showing numbers, this is also very rough things just to give you some ideas. And here I used maybe a bit old figures from 2019 from the IEEE, but there you have like the yearly electricity generation was 27,000 terawatt hours, and so on the left graph I use a logarithmic scale to indicate these numbers of the electricity consumption here, and then I also put numbers of the amount of people in the world, so around 10 billion, and then you have the land area that is available on the world, just all rough numbers, and you can debate about all of them, and then you see. Okay, this goes by itself. And then you see how much area you would need to cover with PV to cover basically the yearly electricity need. And you end up at 160,000 square kilometers, just as a very rough approximation. And you see a certain percentage of that. So that's roughly 0.1% if you look at the axis on the right there. You can do this for different countries separately, just to give you an idea. And then, of course, it depends on the amount of irradiance that each country gets, how much that country consumes. And so, for example, if you look between France and Kenya, I took them because they have a very similar population and they're very similar size. And you see there's a huge difference because, of course, they consume much less, and Kenya has a much higher irradiance, for example. You can also look at other countries, China, Russia, Singapore, which is a city-state, so it has very little land, so you would need to fill it with a lot of PV panels to be able to to fulfill their self-consumption, let's say. Okay, so when we talk about massive deployment in society, so I mentioned already, you have typically utility scale PV, or you have building applied PV, so which is on the roofs. And so there's some benefits to either. So in utility scale PV, you can cover large areas. You can also only take the areas with high irradiance and little shading. On the other hand, if you go for residential applications, it's nice that it's very close to consumption and you don't use additional land, let's say. But on the other hand, you are using additional materials, which is what Stefan explained as well. So it would be nice to combine this and use the materials like the existing surfaces and integrate PV inside. And so you waste as little as possible extra materials and you don't waste additional land. And so that's what people call typically integrated PV, functionalizing existing surfaces with PV. Some people call it PV everywhere, dual use, all these kind of terms that you see happening. If you look at the potential, and this is again some numbers from Germany because they have a lot of numbers available. Here you see the potential for different integrated PV applications. And so, I don't know if so you have, for example, for agri-PV, what Jan was showing, you have a potential of 1,700 gigawatts that you could put if you take the available land for this. For buildings, you have 1,400 gigawatt available. Then you have some urban infrastructure, floating PV, road integrated PV, or vehicle integrated PV with different types, let's say. And that's if you look at these numbers, they are a huge potential. If you can see, if you compare, for example, to 2024, where I looked up some numbers at the moment in 2024 in Germany, 100 gigawatt has been installed now at the end of 2024, and they produced in 2024 70 terawatt hours, which is around 14% of the total electricity production in Germany in 2024. So there's a huge potential for different integrated PV applications, let's say. Well, as I mentioned, these integrated PV, they will result in additional or different challenges and requirements depending on the application. And so I listed here a few, I think the most important ones, and I will go through to show you what is going on, what is possible, for example, in technology, from technology point of view. And so you have this performance is of course important, custom layout is important. If you see what Stefan showed, you have different sizes, so you want to be able to fill up the surfaces as well as possible, so you want to be able to customize them well. The aesthetics can be important depending on the application. Curvature can be important, the weight, safety and reliability, and then sometimes semi-transparency if you use it in a building, for example, where you also need the light, or if you use it for agri-PV, like was mentioned by the previous speakers. So all these requirements can call for adapted technologies and testing that you need. So I go over some, and I start maybe with the custom layout. So you see some nice buildings also like you've seen before. By Stefan, different buildings, they have very specific features, sizes, sometimes triangular. And I show a short video here for those of you who don't know how standard PV modules are made. So this is what is called tabbing stringing. And this is the way of how you interconnect cells in series next to each other. So each time you connect the front of one cell to the back side of a neighboring cell. And what is happening is you place a cell, that's the blue squares, well, the rectangles in this case. Then you draw wires on top or ribbons on top. You solder them together, and then you go to the next one. And each time you make a whole string like that. And you make full strings. And that's the interconnection part of it that you can use in the layup. And that is what is done in typical standard PV modules. So this type of technology is possible, and it's also what Stefan is using in Soltech for some reason, but sorry. And then you end up with a module like this, for example. In this case, you have, if you want to fill a roof slate, and I think it was from Eternit probably or something, a roof slate application. And in this case, there was 3 strings, let's say, that you put next to each other. But you see immediately if you make a, if you want to make a series connection, you go from one end and you need to fill these 3 lines, and you end up with a positive and a negative contact on opposite sides of the module. That means if you want to go to one junction box, you need to bring them together, and you lose some material because of that. And just to show what we are working on is in one hand to allow it to be more flexible, we have a technology which is based on wires integrated in a sheet where you can make turns basically every time. And now, instead of having long strings that you need to implement, you can choose how you go across your whole surface to fill it up and end up, start and end where you want, basically, with some limitations, of course. This is a short video, but it basically shows the same. So what it does is it takes each time a cell, and then it takes a foil with wires, and you do the whole layup to fill up the surface that you want to cover, basically. So each time the robot picks it up, it does an alignment, optical alignment, and it puts the component on top. And that way you can cover a full surface. So nice thing about this is that you can also improve the aesthetics, as you can see here, because we use many wires. They are very small compared to the ribbons, and you don't see them from afar as much as you would see the ribbons, basically. You can also apply this and then go for semi-transparent applications or for opaque BIPV, and this is similar to what Stefan was showing as well. So that is one type of interconnection technology, but you can also think of other types that are being developed, and one of them is shingling, where you basically cut up the square cell into smaller rectangles, and then you interconnect them, not with wires or additional ribbons, anything like that, but you basically put them like roof shingles on top of each other, and this way you also make the contact from front to the back of the next cell, and you can make the line as long as you want, basically, and so you can also fill up a certain surface in a maximal way. Let's say maximize the active area of the module. That is what you see here, and then you can choose if you make just long shingles or if you do what they call matrix shingling or brick shingling, where they overlap also next to each other. You can also leave gaps in between to have some kind of transparency. Another type of interconnection is based, well, there's a whole field basically of interconnection, but this is for back contact cells, and these I don't want to go in detail a lot because it takes a lot of time and it would leave little time for the rest. But let's say back contact cells are a bit different compared to the standard cells because all their contacts are at the back. So while I was saying for the standard modules, you go from front to back of the next cell to make an electrical connection, here everything is on the back, and you can think of different concepts, also do some stringing like for the standard cells, for example, but you can also go for more like a PCB kind of approach where you have a sheet where the interconnection are made and you just pick and place the cells on top, very roughly said, let's say. This is not widely spread yet, but probably this is one of the technologies that will be coming in the future, and it's starting to ramp up in the market as well, so it's important for the future, definitely. Also, the aesthetics is quite nice because you don't have any metallization in front of the cells, and you only have a black surface. So it's definitely interesting. Then I go back more to the aesthetics, to the coloring, and this is also something where what Stefan has been showing. Just to mention, there's different technologies to get some patterns or colors in front. So in these pictures you see different types, but they are all made of films that have a certain pattern or a color, and that are integrated in the lamination inside the laminate or in front of the glass. And so basically always in front of the cells you can make nice patterns like these bricks that you see, or you can have full white colors, these kind of surfaces. Some people also look at putting textiles in front of the cells because they have a certain texture, and people sometimes like that depending on the architect, I suppose. And then a very efficient way let's say in terms of electrical efficiency is using a Bragg reflector on the front glass, because there you can wavelengths are passed through, are transmitted, or are reflected. And so you only you can choose to only reflect those parts of the spectrum that you want to see, so which color you want to have, and everything else can go through, and that's very efficient. Of course, it's a bit more expensive because you need to coat all these layers on the glass. Another way of fusing it on the glass, so printing a pattern on the glass and fusing it inside, so a bit similar as the on the left bottom side, but there it's on separate films, and here you do it directly on the glass and you burn it in. And then finally, there is also some more exotic experiments, and in this case, for example, you see a thing where they, instead of front glass, they put a stone, a piece of stone basically, but very thin, so that you can still, sorry, I try to speed up a bit. So you can have stone, a very thin piece of stone. You lose, of course, a lot in the absorption, but here you have the look and the feel of the stone if you touch it for a facade, so that could be interesting. I will speed up because there's not a lot of time. But so if you go for curvature, it's also an important aspect for some applications, like for cars you want a curved roof, and then typical lamination is pressing it on a flat hot plate. Of course, that's not going to work. You're going to crash your glass, for example, if it's curved, and for that you need to adapt the lamination process. So you can look at having molds, for example, but then it's very specific, and it's for each, you need to make large volumes with that to be profitable, let's say. Another type is going more for industrial glazing, and then you can use vacuum bags which have heating inside, or you can go for autoclaving, for example. There you can also laminate. And then in our lab we have like something which is in between, where you have a double membrane lamination, where you can go from put pressure from both sides and do the lamination like that. Of course, then it's very critical that you build up the pressure symmetrically from both sides, that you still don't crash it. And you also have to pay attention if once you start thinking about laminating hollow structures, that you don't press anything flat in between. Weight can also be an important aspect, and so typical module, let's say glass backsheet or glass is in the range of 10 kilos per square meter. You can think of, if you think of a car, for example, yeah, there you have a steel or an aluminum plate already. Maybe you can just add it at the PV on top of that, and then you can save a bit, because the glass is the biggest part of the weight. So if you reduce the glass and you replace it with some metal sheet, you can reduce the total weight. Or you can, in the next step, also go more for fiber reinforced polymers and composites to replace either the encapsulant or the backside, to even further reduce the weight. And then there's some distinction between how lightweight you make them, and if they're self-supporting still, or if you need some frame around, if you need some mechanical adjustments around that. There's a lot of things on safety and reliability testing. So typical PV modules are tested, of course. You have thermal cycling, you have damp heat, you have humidity freeze tests, and lots more. But these are typical certifications for PV modules. But if you look at different applications, you get additional tests. And just some examples: you do thermal aging at higher temperatures, for example, for buildings and for cars. And the idea is not so much to look at the degradation in performance, but more at problems in the glass. If you have some discoloration or some delamination, if that is happening, that is absolutely not accepted, of course. You also have, for safety, you have sometimes tests, which in this case it's called a ball drop test. Basically, you have a panel of 30 by 30 centimeter, and you drop a steel ball on it from a certain height at different temperature, and you see the test result has to be that, of course, the ball doesn't pierce through, because if you're in a car, you don't want it to go through the sunroof and hit the passenger. The shards or the pieces of glass cannot be too, have to have a certain size. They cannot be too large, too small, too many. They have to stick as well and not fly around. And then also the ball shouldn't bounce back too high, because if you want to absorb the shock, and you don't want somebody else to get hit because it flies off the car. Vibrations are also important in cars, for example, in vehicles, and there's different types of vibrations. You can see like a certain power spectral density for different frequencies. That is like a general test. You can also have shock tests, which represents slamming a door, for example. And then you see, depending on the type of module, like glass is very stiff, but if you look at these fiber reinforced modules, they will have a much bigger amplitude if you have such kind of vibrations. And of course, you want to make sure that the PV survives these kind of things. This is then for a bigger size. This is for a full-size bonnet, the same thing. Because it depends, of course. We can do it for small tests, but if you look for a full-size bonnet, it has a different clamping, so the vibrations will be completely different. And then, yeah, you get the same test. I won't go into detail here. You have typical hail impact tests as well, and that is where you shoot ice balls at a certain size, so typically 25 millimeters at 25 meters per second. You shoot it on the glass on different positions, on the sides, on the edges, in between cells, in the middle of a cell, and you see if the cell is cracked inside or not. And so, okay, we did tests here to replace the glass and go to lighter weight. And you can solve it, but you need to know what you're doing. So you need to have something stiff, very stiff at the backside. The front glass is not needed. It's more at the backside that is important to absorb the shock, let's say. There is also a lot of activities on fire safety and a lot of concerns, let's say. I think maybe Mike will say a bit more about this, but there's a lot of differences in regulations, and that makes it sometimes difficult. Also from the PV module side versus from the building element side, and there has to be some more, let's say, standardization to make it clear. We have also shading tolerance that will become more important with integrated application. Yeah, of course, the more you get into the built environment, the more shading you get. If you start looking at integrated PV for vehicles, yeah, there will be dynamic shading. Also, you will park it in different places, so you will not know up front where the shading will be. So it has to be as shade tolerant as possible, not only for the performance, but in fact, mostly for the reliability to avoid hotspots, because you can get damage you can damage your modules, or it can become a safety risk in the end. There's different ways of dealing with this. Yeah, okay, I will not go into detail. And then the semi-transparency, if you look very long ago, people were first making holes inside the cells to make some semi-transparent. You can also think of making smaller cells and interconnecting them, and this is a few ways of doing this. But the mostly people like Soltech also is making full-size cells, and they put some space in between. And from far it works, of course. You can also look at spectral control, like I mentioned, for the Bragg rating, for example, to determine which wavelengths can pass and which wavelengths are reflected. And it can be interesting for some applications like IEEE or for cars where you want to reduce the car overheating, for example. I have a few. Yeah, time's up. Okay. I think that's fine. I can stop. The rest is the next.
There will be time for questions, definitely. So I would like to introduce Maaike Bergmoes. She's principal facade engineer at VK Engineers, part of Sweco, and she's been working on building design and construction. I think that's very important. We discussed about building integrated, but like, okay, how do they actually do it in practice? And also the safety. Well, I know almost nothing about it, so I'm curious. Yes.
Battery. Shall I put it in my computer? but then the pointer is not working. Yeah, okay. I'll do like this. No, 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 it's okay. It's okay. I will stay here. Yeah. Okay, hi. Last effort, I would say. So I'm going to quickly introduce the company. Myself, I started at VK Architects and Engineers. It's a big engineering architectural office in Belgium, 600 people. And then 2 years ago, we were bought by the Sweco Group, international, the biggest, one of the biggest international engineering firms. Yeah, we are 21,000 engineers and architects, so it's like there's always space for new people, apparently. So, and we are divided in big divisions. It's Buur who is doing like master planning, infrastructure, pharma, industry, energy and environment, and buildings. Myself, I'm responsible for the facade engineering in the buildings division. So we actually assist architects and clients on all the technical issues with of the facades. In buildings, we are next to facade engineering. We are doing the structural engineering, the MEP engineering, acoustical engineering, fire safety, yeah, whatever you need to build a building or to design a building. Okay, facade engineering. So we are helping architects and clients to get this facade, to design this facade, to be that it's buildable and that it's that clients can pay it, so that it's within the budget, so within the architectural intent and within the budget of a client. So that's the most important thing. And then we help the architect to really assist on the technical level on wind, water tightness, energy, the component to the energy. How is it fitting with the energy concept of a building, but also about maintenance and replacement. How are we going to replace, how are we going to build in replacement strategies in our detailing and stuff? How are we going to build it? Are we going to prefabricate it and stuff? So that's what we are assisting with. And then, yeah, BIPV, that's really the facade. So it's a PV, and it's actually a requirement of the energy concept of a building that is totally touching the facade. So we are then actually interacting with the architecture, with the HVAC system, with all the electrical components, energy regulations, fire safety, and so on. Okay, it can be whatever you want. BIPV can, if you see, it's like a conceptual vertical section you see, and the green one can be the BIPV component with lots of reference examples. You will see lots of examples that were already showed in Stefan's presentation, because sometimes we work together also in the end. And it's about all colors, so we have lots of samples in our office to work with the architects, how we can build up this architectural intent together with the wishes of the architects, colors, and so on. BIPV, it's like PV that is becoming a building component, and that's really important because it's actually, as soon as it's a building component, it's integrated in the facade. It needs to withstand the water tightness, air tightness layers of your building. Sometimes it's not only always the airtight component of your facade, but we have to check thermal fracture, condensation, fire safety, durability. We also have quite strict architectural and visual requirements for facade systems. Flatness, decolorization is like needs to be guaranteed for 30 years. All these kind of things are giving us extra standards and requirements to take into account. And it was already said that we are doing like the technical requirements for the facades, and then the electrical engineer is writing the specifications for the electrical component. But these two are, glued together. So it's really a collaboration of all the engineers and architects to have then the end optimized solution. So it's like a PV component that is becoming a building component, a facade component. I've listed a bit all the specifications that we have to take into account. Then together with sometimes, most of the times it's an add-on, the PV requirements, but sometimes we also have some conflicts in both of them, the PV requirements versus building requirements. Some examples is if you have a standard PV, you're thinking about the first class of 2 or 3 millimeters. If it's like a BIPV product, it has to fit the wind resistance. It needs to be flat even if it's bended, so deformation cannot be very big, meaning that you get glass compositions of sometimes 8-8. Or 12-12, up to 12-12. So that's a totally different weight and product you see directly. Sometimes it's integrated in double glazing and triple glazing, double laminated, very complex compositions. And then fire safety, it's one of the examples where I say, okay, you have the PV standards that we all know, but then the building standards, building component standards can be totally different. If we are speaking about PV fire resistance, then you have an international standard that is like classifying PV into A, B, and C. If you go to the fire resistance classes of building components, it's totally different. And it's tested according to different testing methodologies, meaning that a class A in an international standard, the IEEE, the first one, the middle column, a PV panel can be a class A on a certification, but in tested according to building standards, it's falling actually in a B classification. So you see directly that sometimes there is like a miscommunication in the building world next to the PV, standard PV world on certifications with a certain classification, which is not like the same classification according to the same testing. It's just one example of things that we have to take into account. If you have questions, I can explain later. I wanted to show a bit the BIPV projects that we do and how we are building this up. So it starts in the beginning with the first idea of an architect, and the architect wants a certain architectural concept, and then we think, okay, how can we integrate BIPV? And we are doing quite quickly some feasibility analysis to have the big numbers of what can this produce and how much does it cost, what is the ROI of this, the payback time, to start to talk with clients if they want to take, sometimes it's really, if they want to take the risk to add BIPV to their project. And then together with the architect also, is this something that I want on my building? How can it look like? And then renders are getting built by the architect, and we are moving towards more detailed calculations, for instance. When you're actually in the beginning of a project, together with the architect, you have an open, it's like a white page, meaning that you still can work together with the architect on the window to wall ratio or the percentage of the width and the height of an opaque part of your building, of your facade. And then for instance, we have built a script that is really optimizing sometimes the opaque parts to have as much as possible cells on your facades, meaning that according to the cost, BIPV is always like, it costs a lot, so you need to make it as efficient as possible. And this we do together with also energy calculations on, okay, how much percentage of transparent glazing do we need to have a good daylight entrance, and how much percentage of this window to wall ratio is good enough for cooling system for the blocking of the radiation, for instance. So all these things are coming together in the design of, in the technical design of the building. I've added this slide just to show that we do think about retrofitting old buildings, retrofitting. Some buildings have a fully opaque facade, which is not insulated yet. So then it's worthwhile to do analysis of this facade. Is it not, is BIPV the best solution for this project? Moving up to projects that are already built. And this one, Stefan also showed. A project in Brussels with BIPV on vertical louvers. Then an old building also, restoration of a building where the light sky, we've replaced it with BIPV glass, double glazing, transparent. And then just to show that again, this technical, it's becoming a building product, so you have to check durability of materials. How hot does it get, this glass layer? And does your glass edge can stand this extra temperature? Does the glass not pumping too much, for instance, due to this extra layer of all these kind of things are then analyzed on component level during the design of your building. In this one, for instance, we analyzed the temperature going through the BIPV, hitting the old structure, which could not take extra temperature for the thermal expansion of the structure, for instance. So all these kind of things are coming together in a final solution of a BIPV product. Another one Stefan showed, where then from the engineering side, again, we are checking this durability of the materials, of the temperatures. The BIPV layer, the white BIPV layer component, it's actually on a fin, and it's hiding, or behind the fin, there's an air intake for the HVAC system. And then the question was, how hot does this cavity behind the fin and the BIPV panel is becoming? And can we use this air that is with a higher temperature for the air intake, for the natural ventilation? So all these kind of things so next to the component of the BIPV, you need to also analyze all the other effects on your building. Okay, and then the final one, which Stefan also showed. You can also see that actually when we are talking about BIPV, it's not that we have like 100 competitors. So lots of times we work together in the end with Soltech because it's a local partner, which is also important for instance, replacement and lifetime of your facade. So the ZIN, maybe that's one also to show you a bit how a design of BIPV is getting built. It's like we do solar radiation analysis, and then you define the zones where you have the highest solar radiation, so the most potential for BIPV. And then you can see, for instance, on the, it's the east facade, that you have like a bluer zone of the shading of the tower that is next to it. I don't know if I can, yeah. And yeah, like this, huh? So here you see, so we've actually analyzed this and said, okay, underneath this line is actually too expensive to add this layer of PV, and then in the end you will see. I will show you some pictures of the installation itself, but you see that here we don't have the louvers anymore. Okay, we have louvers. You can see here. It's really, this is the zone of the shading, where actually it was not beneficial anymore to put BIPV louvers. We have here on top vertical PV that are integrated in the facade panels. Here you have transparent PV in the light sky, skylight. Wait. And then on top, to cover actually the HVAC systems and all the technical installations, we also have a PV roof. This is with typical standard PVs. This is the integrated panels. And here again, you can see a bit the louvers. This is on the east facade, which is not fully covered with the louvers. And on the south facade, it's really covered fully with louvers that are also giving shading to the internal one. So it's really connected and designed to have the best solution also for the cooling system. And this is one big panel installation, for instance. It's a 2-story high zone where 5 louvers, BIPV louvers, are installed. So, and then that's how we install this prefabricated facade panel with BIPV. And then all the electrical components are already integrated in the profiles and stuff. So you have like a panel that is installed. And then later on, with a meter of a cable towards the internal rooms, and then later on, when all the facade panels are installed, the electrical engineers and contractors are then connecting every cable towards the internal installation. Okay, that's it. Nog een beetje voor willen doen.
Before going to the panel, do you have any questions for Maaike? Yes.
Well, it's great to see that nowadays architects can be architects while we're still sensible and placing PV on top of these surfaces, these organic surfaces that the architects are now creating. And also in the final building that we saw, where there is variable shading. What I was wondering, however, is while you can put a lot of PV on the facade of buildings and well, on any type of surface, basically, the real place where the most where it is determined how much energy can be extracted from the surface is not the facade itself, I would say, but actually behind the facade, how all these PV panels are connected. And you briefly touched upon it in the final slide, where you said that these electrical components are inside this module. But what does that mean? Does it mean that each panel, or each panel in this case, has a separate converter so that it's connected through all these small micro inverters, or?
It's calculated. It's like also what Stefan is saying. So we are calculating also a bit to do with the fire safety. If you have, for instance, a project which is reachable by the fire brigade, then building that I showed, we will stay at the outside because it's reachable everywhere. So you have to think about how can we get there when something is wrong, when we measure that some panel is not working. And all these kind of things need to be combined for the final solution. So it's not a one solution, it's always, it's BIPV, it's project specific. I think, Stefan, you can say that you're not using a panel for one building on the other on another building. It's really always, it's a project specific, and even what Jonathan was sometimes we also even integrate if we know that some zone of the panel is like 40% of the time in the shade, then we can think about integrating with the panel also some smart stuff. So
Well, yes, that's actually my main question. Given your expertise and experience, do you most often go for microinverters for each panel specifically, if you have especially these organic architectures where every single panel has a different irradiation? Or do you combine them more and then have a less efficient MPPT?
At the moment, most of the systems are still string inverters.
less efficient.
Just
I think
bit less efficient,
yeah.
but the cost in
It's
having
the cost, yeah.
it's about cost. It's also about reliability. If you have a microinverter or an optimizer behind your panel in a zone that you cannot reach, which will have certainly high temperatures, we're taking a risk that is for me at the moment too high. So, but that's personal.
We offer,
my clients, I don't advise.
That's a great answer. Thank you.
Big difference, but from consulting point of view, we advise not to integrate microinverters. We have now a project where they have asked it, and they will all be inside. That means every panel we will get into the building, and the microinverters will be installed on the inside, reachable from the inside. Yes. Because of temperature and reachability. But then the cost is crazy. Okay.
Because you always have to, you have a client who has to pay. And who really is like, oh, I don't want to take any risks. So if we integrate something smart and something that we have to study it very good, and it needs to be cost efficient.
It's also depending on the rules, I understand. I had practical experience with the student in Switzerland, for example. There was an insurance company, they made some rules, and one of them was that all the, let's say, the electronics, the converters should be in the basement or on the lower floors, and then it's not allowed to do it even. But it's really sometimes country specific or
and sometimes it's like you have designed everything, and then the fire brigade of a certain city needs to sign off, and he said, oh no, I have had somewhere a fire, and then you're like, okay, you have to redesign and put some more conservative solutions in place.
I think we all agree that we are ready for the discussion, right? So this is the last part of the event. We are going to be led by Professor Johan, which has plenty of experience on all these topics. Please, I'm going to just...
Okay, good. Maybe the three remaining speakers, if you can come over here. Thank you for being so brave that you want to stay. Oh, I'll stay up. Okay. Yeah, and I have 10 minutes left, I think, or is 15 to 12. Okay, good. Let's see. Now, to be honest, first time I heard about BIPV was exactly in this auditorium. Guess something like a bit more than 30 years ago, to be honest. There was a guy van Overstraat, some of you still remember him, who was telling me about it. And I was a student there sitting on a very uncomfortable wooden bench, because you guys don't realize how comfy these seats are these days. When Stefan and I were sitting here, it was something else. But okay. And yeah, it was the big promise then, and it still is the big promise. I understand, because actually I was in that area this morning with that fancy building there near the Noordstation, and it was the only building around there with PV as far as I know still. Huh? The only one, yeah. what do we need to do? What do we need to change to make this the standard in these buildings? Huh? Yeah. Okay.
No, no. I can just very generally. I think what I was putting there was that still the cost is quite high. So for these big projects, that's still doable. But if you want to do a wide-scale deployment, the cost still needs to go down. And there's a few things. And one of them is what I wrote down, because we were in a project together, BIPV for All, where one of the things is that there's a lot of overhead in the pre-design phase, let's say, where you have the building constructor and the architect and the customer and the PV module producer trying to align everything, and you have lots of discussions back and forth on what is possible, what is not possible, and this part is a bit what you showed, which is in the software. What is nice, I think, that you can screen a lot of options that are there directly in a database where you know it's available from. So that's one of the things that could help, I think.
Yeah, because the big problem when I see from the design part is that you start with, and that's for all the components of a building. You start with a client who and an architect who's saying that's the idea. How much will it cost, and how much will it produce, and how much will I lose? Will the demand for heating and cooling be? And so in the beginning, you do this with the big numbers and from a conservative side. So meaning that for BIPV, you start with, oh, I'm not going to take the highest watt peak because I don't know, maybe the architect will in the end choose a wide panel. And then I overestimated my watt peak. And on the other hand, you also choose a conservative budget. And when you look in the overall measures of a building, then at the moment the BIPV solution is like at the bottom of the list, because you have more measures with higher potential, with lower risks, with lower budget to performance, and that's the starting point.
Hi.
I'm quite optimistic now because, first of all, PV is there to stay. PV became a lot more affordable than 5 or 10 years ago, certainly 30 years ago, if you're referring to that period. And mostly now we have just rules which impose the buildings to be energy neutral or closer and close to energy neutral. And so somehow, sooner or later, they will need the photovoltaics. And it's already now for some buildings that they need us, and it will become year by year more. So for us, that's the basic also why we did the investment now, because we know it will not be because it's profitable, but just because you need to be self-sufficient, more or less. She's not agree 100%.
Not fully, yeah. Yeah, because in the end we also need to look not to a one building that we are designing and paying, but on a grid level, on a master planning level. And we see that building owners who are planning to do a tower where, a tower, you don't have the roof, so you need to think about a facade. But then they have maybe a zone somewhere else that they can put a more, the standard PV or another way of renewable energy production. So yeah, it's a very good question because
to continue on that, isn't it also a trust issue, a reliability issue, because these buildings will be standing there for decades? How do we guarantee that?
If I can make the example of standard PV and other renewable energy measures. You guys know the ESCOs, the third parties that are financing certain components on buildings, because they can then take the energy and sell it again. So it's a business model, financial business model. If you see, they are doing it for almost every renewable energy measure, but then for BIPV, they are saying, no, because it also needs to take into account the water, wind, air tightness of your building. It's about temperatures, higher durability issues. And so these are really the risks. It shows that it's a component with risks which we can solve fully. But that means that you have to always convince a client that we can solve it. Yeah.
Oh, yeah.
Fine, fine for me.
Yeah, but Stefan, what
proving it
lifetime
now.
do you guarantee these days to the products you sell?
We give 25 years warranty on the production output, and we give a 10 years warranty on the product itself, which is in building construction 100% standard. So we give the same warranties as other building elements, but indeed it takes time to convince the market, and that's what we are doing now with all these references, with the project we have done, which are working fine, and so it will come. It's just a question of time. You have to be patient, you know.
Yeah, I think it's a question of time in a way, because also if you look at standard PV modules, there's a lot of them out there, but even now there's changing cell technologies, for example, and people are very reluctant to change. They're not sure if it's bankable because of these reliability risks, and it just takes a few people to start up pilots and then gradually growing, and it's just convincing the banks that it's reliable. Even if you know up front that it's reliable, they won't believe you until it's there. And there is some, I mean, from PV side, there is also increasingly attention for quality even in the field. Now they can use like techniques like photoluminescence to check whole fields and see where the modules are degrading or not, which was not possible in the past. But this is kind of, I think, forcing also the manufacturers to be looking at it. And
does that mean we have to design for easy replaceability then? Because now you guys can see, on the 18th floor, number 3 from the right has a problem.
Well, that's one of the things, but hopefully that forces the manufacturers to make sure they checked it already before it's up there and minimize the risk on that.
And there's a whole, when we look what we have to do with our buildings in the future is really to extend lifetime of our buildings. In facades, lifetime of a building in a life cycle analysis is 50 years. For facades, it's like 30 years. 30 years is like nothing. And then clients start also because it's like a rapidly evolving technology. So they are saying, if I am paying now that amount of, will it then in 5 or 10 years time not be an old PV panel in which then there is already an alternative that is producing much more, or I don't know. And this is really something that we try to integrate also in the design, smart technologies, in the sense that if there's a turning point of a new technology which is much better, that there is a way of dismantling and changing the material, for instance. Yeah. But then it should also be considered the embodied carbon and the recycling of the components and the materials itself, which is also a big issue, I think, with PV panels. So it's really a big, you have to look to all the parameters for this decision.
Jonathan wants to say.
No, not recycling even. I just want to make the discussion a bit more complex, because of course we're talking, it really depends on the application as well, because we're talking now about buildings, obviously, because that's also a key point. But if you're talking about integrated PV, you could also think about vehicles, and there the story is quite different. I mean, the lifetime it has different issues. It will be much lower than what is standard PV, and so it really depends on the application. It's not a one answer that you can give on all these things.
John, I have a question for you specifically. By the way, when I saw your presentation, I always thought IMEC had clean rooms, but it also seems you have rage rooms, where you can rage rooms where you can destroy everything. Okay, but some years ago, I had the impression the way to go was transparent cells. To put them in windows and you see, it's all a lot of glass. But I have the impression, yeah, now the trend is just go for a standard color. Is transparent cells still on the research roadmap? Because also in the modules that I saw that were installed, it's solar cells and then a standard window.
Yes. No, it's definitely still a research topic, and you know, maybe the perovskite, for example, has a big promise in this, in being semi-transparent itself, because it's very thin layer. It can be efficient as well, but it has some issues still to overcome in terms of reliability. There is also still some projects like, but also always thin film, of course. With silicon, you will never be able to do that, but with thin film, there is some options. And indeed, ideally, you would have a window, and everything that is not that is outside of the spectrum that you can see, it could be recovered into energy in theory, but in practice, we're not there yet.
Okay,
I'm
good.
afraid.
Now another thing that is a bit more a problem in these kind of applications compared to quite standard building added PV is there seems to be a lot more shadowing. Yeah? Shadowing. Static shadow, but maybe also dynamic shadow, like in your vehicle integrated PV. Is that a problem in practice?
Well, yeah, you have to take that into account to protect against these hotspots, also for the performance. And there is quite some activity now on making shade-tolerant modules, also for agri-PV, if you put them vertical, for example, these things. In vehicles as well, and there's a few options like increasing the amount of diodes, these bypass diodes, and ideally you may want to have one per cell, but of course that adds to the cost, and then the question is that always useful? Because if it's not being used, it's also a reliability risk if you integrated it, and it's a cost. What is maybe another option, what is a very promising one, is to have it inside the cells. Some cells, these hotspot risks is coming from the reverse breakdown voltage of a cell. If they make it low enough, then these hotspots would not be such a risk, and then you could have kind of a bypass diode per cell integrate, and that could be one option. But maybe, I don't know.
Stefan, do you sell this already?
We sell it already, and what we do now in the design of our panels, we have in our panels most of the time more hotspot diodes than in standard PV panel, because we have the choice. We can make the pattern, and if instead of just simple example, you have a panel of 1 meter by 2 meter, instead of having the strings in the length and having a diode on top every, let's say, 24 cells, we prefer to do it in the other direction, which gives us more possibilities to have diodes integrated and to be a bit more shade tolerant. And I have to say, to be honest, we don't do that as much from a performance point of view, because in terms of performance, this partially shading on a module, essentially on a yearly base, it's quite reasonable. But we do that more from a protection point of view of our panels, and so that's more about fire safety, lifetime, things like that. So we have the choice already now, and we do it already now. So internally, the instructions are very clear, foresee more diodes than purely from a theoretical point of view necessary. We have been doing the tests, and we know that our aging of our product is less if we integrate more diodes. And so we do that. It has a certain cost, and it's also a cost that you can explain to the client. If you have competitors who say have a certain design, if you explain to the client, look, that's why we do it, it has a better performance, we have a better warranty, and then they can say, yes, but the warranty of the other is the same, yes, but it takes a higher risk. And most of our clients are sensible to that. And it's again about explaining, and that's why bigger projects nowadays are more common, because we still have that explanation to do, that negotiation, that things, and that's why we pass by for the moment with bigger projects.
Okay. Maybe a question for Maaike. I saw your movie about how these modules were installed, and honestly, it doesn't seem to be very reassuring. It's not very reassuring for me, the way these things are being handled, because, when these guys are being filmed, they do it nicely, but when you're not filming, I don't want to know how they are installing it. But can standard
we check.
building... secret camera. No, do the standard technicians that you have out there, can they install all of this stuff, or do you need a new kind of technicians? Do they need extra training?
No. Because they know the installation of a standard PV installation. They know it quite well. It's also written in the specifications how to install. And yeah, sometimes I think, Stefan, we saw in the project that I showed, we saw on certain moments the full design team got a picture of, I think it was like 2 meters by 2 meters bunch of cables without labeling. And then the electrical contractor, he needed to like figure out which cable came from which panel and yeah, okay, sometimes things happen on site. You cannot avoid it. But most of the time, it's like if everybody follows a bit what is designed and what is written in the specifications, it goes well. It's also not, correct me if I'm wrong, not so much different than a standard installation as soon as you're inside with the cables. So, yeah.
I think the problem is getting inside with the cables.
Yeah, but the getting inside of the cables, it's really, that's why we are doing prefabricated panels.
Yeah.
So because indeed you go with a small hole through your water tightness, through your insulation barrier sometimes, through all these things that normally needs to be tight. Of your facade. So all these components and the connections through these profiles are really designed with components that are fit for making this connection, making the fire barrier, because you're also sometimes going through a fire barrier. And so all these things are designed for BIPV installation. And it's most of the time at big projects, it's prefabricated, done in the factory, quality control, all these kind of things. I think you go sometimes to a factory to check the installation of your panel because you have to guarantee the production. And if a facade contractor is doing something wrong with the installation, then you're maybe to blame partially. So it's really checked and controlled and designed.
And nowadays you have to know that when you construct a building, everything is drawn in advance. You have your BIM system where all details, every cable, every millimeter of your construction has been pre-designed. So we can really upfront walk through, and it's literally with your mouth going through any detail, really looking at it from every side. Where do we pass through? Is there no conflict between our junction box and a screw which mounts whatever? And so all these details are really, and it's totally different than 10 years ago. Not further than 10 years ago, you still had construction. And we still have it now. For example, we have now a project in Morocco where the size of the glass comes in after construction of all the rest. It's not the case anymore in Europe. In most of Europe, you have fully in advance. Every millimeter is counted. You still have some measurements to do because not all subcontractors are doing.
There are some tolerances.
But there are some tolerances, but in general, most of the details are really pre-designed in BIM models, and every subcontractor has to stick to it. Otherwise, he gets penalized because you cannot afford to deviate from what has been foreseen. And that BIM model is drawn by companies like Sweco.
Okay, maybe a final question. I have the impression. We are.
He's getting nervous.
5 minutes. Oh, okay. Oh, okay. Yeah, good. Now.
But what you are saying is good, I think, because that it's being tracked and that you know what is where. Because for PV, the image is important, I think now, especially. I think Maaike, you showed in in a previous event, you showed there was on the news a fire in Brussels, and there was some PV around it, and of course everybody started blaming it's PV, and in the end, I mean, it's probably not related to the PV element, but it's very important, I think, in this very early stage, especially because otherwise people will turn away and say, "See, look, it's dangerous. We shouldn't put it." And that's what we can.
Good. Totally different question. You already mentioned that. Yeah, you have to. You're dealing with a complex legal structure as well. It's a big building. You use ESCOs. The ownership is very complicated because you may have multiple owners, renters, whatever. And then you install a sort of joint PV system, and that's already a problem with standard PV panels. And for that, people want to start up energy communities or whatever, sharing systems. Do we still need different business models for these kind of systems as well? Will that be part of the solution, maybe?
Yes and no. I think there are already a lot of these systems existing, like you said, with co-ownership and things like that. So I think that's what we call non-technical barriers for the market. That's what you're referring to. A lot of systems already exist, and I have to say that the legislation is moving quite fast. So the laws are moving to allow this kind of combinations of ownership and responsibilities and things like that. And I think from a legal point of view, it will go very fast. The last barrier will probably be insurances, because they're always the last to adapt, and they are quite risk-averse, and they don't have statistics, so they cannot calculate. And so for me, it's going quite fast. Legal, it will go fast. From a financial point of view, the benefit is there, so there are more than enough interested parties, third-party investors are interested, they're looking at it. I think the last barrier will be probably the insurance companies to convince them that we are safe, and that's why we do all these projects now, just to prove them that there is no problem. And that's, for me, the last barrier to take. Another point of view on that?
Well, it's going fast, but on the other hand, like we've seen the Brusilia Tower, the old tower with one south wall. Okay, then you have all these different owners. I don't know how it's called in English, but you have the Vereniging van Mede-eigenaars in Belgium. So part of them, they already don't want to invest in something. I don't care.
But they changed those rules.
It's not my. It's not my wall. So why should I put money in? And then on the other hand, we discussed on this before the meeting. Now everybody can hang on their balcony and plug-in panel. So yeah, legislation will have to follow very quickly, because otherwise you will get like patchwork buildings which are not fitting. Brusilia is a tower that is connected to erfgoed, a heritage. So heritage is like they are really very strict, and everything needs to stay identical, and but then there will be now a patchwork which they don't want.
But
so
I was walking around there in Brussels this morning, and I was wondering where the hell were those guys when they were installing these satellite dishes around here.
Yeah, but that's the same thing. That's the same thing. And then legislation also pushed us towards not decentralized HVAC cooling systems. So okay, they will have to follow, because that's like an open field.
Maybe last question for the three of you with a very short answer, and then we can round up. We saw so many nice photos, examples, renders, whatever. But can you pick one integrated PV technology that you saw, or maybe that you demonstrate, that you think will be in 2050 sort of the standard on all buildings? Your winning product?
I think it will be ventilated facades, fully covered with cells, with a certain opaque color, which will be then decided by the client what color he wants in function of the performance he really needs. But I think the closed, the ventilated facade, because there you can also go to kind of semi-standardization. You could, the mounting system can be standardized. Also the size of the panels can be partially standardized, not around the windows maybe, but the bigger parts can be standardized. And I think that will be probably the most promising technology for the coming 10 years.
You agree?
Yeah, I agree.